Alright, so the first thing we want to do is use the unit circle to plot the graph of f of theta equals sine theta. So the first thing we want to note is when we're graphing these, it will almost always, in fact I can very rarely ever think of a time we will use anything but radians. So remember, if we don't specifically say otherwise, we will assume radians. And as we talked about last week, we know that there are 2 pi radians, or about 6.2 radians, in one trip around the unit circle. So we want to use these values to help us plot the sine function. So I'm going to go ahead and use some of the values that we have already here. So things like 0, pi over 6, pi over 4, pi over 3, pi over 2, 2 pi over 3, 3 pi over 4, and 5 pi over 6, and then we get to pi. So if we grab our unit circle, remember on the unit circle that sine was equal to y. So we look on our unit circle, and we're going to rotate to our first angle, which is pi over 6, so we go to here, and we're going to look at the y-coordinate. So the y-coordinate on our unit circle at pi over 6 is 1/2. So the sine of pi over 6 is going to be 1/2. Oh, I missed the first one. So at 0, we look at our y-coordinate, and our y-coordinate is 0. So the sine of 0 is 0. The sine of pi over 4 on our unit circle is going to be 1 over the square root of 2. Pi over 3, we go to here, we go up to square root of 3 over 2. So root 3 over 2. And at pi over 2, we're going straight up. That's the same as 90 degrees. Our y-coordinate at that point is 1. So then the sine of pi over 2 is going to be 1. And then we start our trip back down on our unit circle. So 2 pi over 3, 3 pi over 4, and 5 pi over 6. Looking at our y-coordinates, we have root 3 over 2, root 2 over 2, and 1 over the square root of 2. So these are mathematically equivalent, but I'll change it to root 2 over 2. And then we're going to descend back down, so root 3 over 2, root 2 over 2, 1/2, and then at pi, we finally get back to our y-coordinate being 0. And then we start our way down, and we're going to have the same values again, 1/2, root 2 over 2, root 3 over 2, and 1, but this time in quadrants 3 and 4, y is always negative, so we're going to get these negative values. And we'll notice that there's some symmetry here with the angles in the first quadrant. It's just they're negative, so 1/2, root 2 over 2, root 3 over 2, and down to -1. So let's start plotting these points, and to do so, so let's go ahead and get some approximations of things like the square root of 2 divided by 2 is going to be about 0.71, and root 3 over 2 is going to give us 0.866, so 0.87. Ish. All right, so we have 0 and 0. At pi over 6, we're going to jump up to 1/2. And then at pi over 4, we're at 0.71. About there. And at root 3 over 2, we're at pi over 3, we're at 0.87. That's going to be here. And then at pi over 2, we get up to 1. And then we do the same thing on our way back down. 0. So that gives us the first part of our sine function. And then we would do the same thing for our angles as we go through the values. But as we talked about, we're going to get the same values again, but this time they're all going to be negative and cycle back up. So we're going to get these same values all being negative, so we go to a half, and is a negative 7, then we go to 0.87, and we go to 1. I think I'm up too far. Let's try that again. Let me do the same thing again. And we get our wave coming back around. So, a couple of things we want to note. We've now graphed our sine function from 0 to 2 pi. So what's going to happen at this point? Well, we went all the way around the unit circle and we're back here. So what's going to happen if we keep increasing theta? Well, we're going to start hitting all these coterminal angles. So if I were, say, at 13 pi over 6, 13 pi over 6 minus 2 pi is pi over 6. I'm back to where I'm going to repeat that same pattern again and again and again. So we'd mentioned last week that these functions are periodic. That is, that they repeat themselves after a certain amount of time. Well, so at least for the sine function, we're going to see that the unit circle repeats every 2 pi. So then we would just start this whole process over again and again and again. So you'll have this wave that goes up and back down, and it would continue forever in both directions. So that gives us our graph of the sine function. All right, so now it's your turn. I would like you guys to go ahead and draw a sketch using the same idea of the cosine function. All right, so we identify our A as this value right here. So the amplitude is the absolute value of A, which is the absolute value of negative 6, which is 6. Since A is negative, the graph is reflected across the x-axis. All right, now we want to talk about horizontal stretching and shrinking and reflections on the y-axis. So this is where we are going to be using function composition. So now instead of sine x, we're going to have sine of some function of x. So a regular sine function is the black one that does this. That's our generic graph. For sine x. And if we look at the sine of 3x right here, so it's composed with 3x, we look at our blue wave and we notice something very, very interesting. So they have the same starting value, Well, my blue wave in the time it takes for my black wave to cover one period. So one period for my black wave is from 0 to 2 pi, is from here to here. How many times did my blue wave go up and down? Well, the blue wave came back to where it started, up, down again, 2, and up, down again, 3. So this went through one period, and this went through 3 periods. So when we did the composition of sine with 3x, what effect did that have on our wave? It caused it to go through 3 times as fast, right? When you replaced x with 3x, the argument inside the function increased by a factor of 3. Therefore, it went through 3 periods instead of 1 period in 2 pi. So the composition is going to change the period of the wave. So the period of our new wave is going to be 2 pi divided by b, where b is the coefficient on the inside. And if b is less than 0, it's going to reflect the graph across the y-axis instead of x. So the bigger the number is inside the trigonometric function, the faster the wave is going to move. Therefore, its period is going to get smaller. Remember, the period is how long it takes it to go back and go through one cycle and come back to where it started. All right. All right, so our period is given by the formula 2 pi divided by b. And in our case, our b is going to be 2/3. So we're going to get the absolute value of 2 pi divided by 2/3. And then, since they're all positive, we don't need the absolute value. And we can make 2 pi into a fraction by putting it over 1. So then we have 2 pi over 1. And a fraction divided by a fraction is we multiply by the reciprocal. Our 2's reduce out, and we get that our period is going to be 3 pi. So after reducing, the period of that sine function would be 3 pi instead of 2 pi. All right, so now let's ask ourselves the question, well, how are the graphs of sine, so f of x equals sine x, and g of x equals to the sine of x minus 2 pi related? Well, in terms of what we know about parent functions, what would this represent? Well, what is the x minus 2 pi? Well, this is a horizontal shift. So since we're subtracting, it's going to go right. How far? 2 pi units. Well, wait a minute. What was the period of the sine function? Let's grab our graphing calculator and do an experiment. So if I go y equals, and I go sine x, and let's change our window up a bit. So that's fine. Let's leave that from negative 10 to 10. But let's change our y min to negative 1 and our y max to positive 1, and change our x scale to 0.1. So I graph it, and I get something that looks like this. So as we talked about above, this is 2 pi periodic. So it repeats itself every 2 pi units. So this is my graph y equals sine x. Well, if I were to graph, let's just change it, y equals sine x minus 2 pi, and I graph, what do we notice about these two graphs? At least in my opinion, they look exactly the same. Well, that's because if it's a wave that is 2 pi periodic that extends forever in both directions, if I grab that picture and move it over 2 pi units, what's going to happen? It's going to land exactly on top of itself, and we won't be able to tell the two graphs apart. So shifting a 2 pi periodic function 2 pi units to the right or the left is going to produce an identical graph, because x is coterminal to x minus 2 pi. In fact, for any angles that are coterminal, so any multiple of 2 pi plus or minus, will result in exactly the same graph. So one thing we do have to be careful about when we start talking about shifting them horizontally and vertically is that if we have a horizontal stretch and a horizontal shift, we have to be a little careful when we calculate them. So our warning is, when both b and c are present in the formula, we must factor out b before calculating the horizontal shift. So in symbols, if you have a function of the form sine bx minus c, we need to rewrite it as sine of b times parenthesis x minus c over b. So what this is really telling us is we have to factor it to where inside the parentheses the coefficient on the x is 1, and then the horizontal shift is c over b, not c. So find the phase shift, aka the horizontal translation, and the period. So the first thing we need to do is rewrite this as the sine of 2 times x minus, and I'm going to come over here. We have pi. We can make it a fraction over 1. We want to factor a 2 out of it, but it doesn't have one. So we multiply the top and the bottom by 2 to create an equivalent fraction. So then if I factor the 2 out of the numerator, I get a minus pi over 2. So then this gives us that the phase shift is pi over 2 units right, and the period is 2 pi divided by 2 in absolute value, so that's just going to be pi. So, as the warning indicated, our horizontal translation, aka our phase shift, isn't pi in this case, it's pi over 2, because we have to factor the coefficient off of this. The other thing we could have recognized, if we recognize this as bx minus c, our formula tells us that the horizontal shift is c over b in this case, which would have been pi divided by 2. So we get the same thing either way. All right, so we identify our values a, b, and c. So if we factor out our -4, we get f of x is -3 times the cosine of -4 times x minus pi over 4. So the phase shift is pi over 4 units right, and our period is going to be 2 pi divided by b, and our b is -4. Gives us pi divided by 2 in our absolute value. So our wave's going to have a period of pi over 2, and it's also, since b is negative, the graph is reflected across the y-axis. All right. So now let's put them all together. So we wish to determine the midline amplitude, period, and phase shift of the function y equals 5 cosine pi over 5x plus pi minus 2. All right, so let's clean up the inside first. Let's focus on this for a bit. So we have pi over 5x plus pi, and if I factor out a pi over 5, that's going to be x plus 5. So then this gives us y equals 5 times the cosine of pi over 5 times x, but I have a minus sign in my formula, so I'm going to rewrite that as a minus 5, take away 2. So now I can identify each of my parts. So my amplitude is going to be 5. my period is going to be 2 pi divided by pi over 5 in absolute values, making 2 pi a fraction over 1 gives me 2 pi over 1 times 5 over pi, which is 10 pi over pi, which equals to 10. My phase shift is going to be -5. So minus minus, so it's going to be shifting left 5 units. And then lastly, I've got the -2. So that's going to shift down 2 units. So the midline is y equals to -2. So it's going to be a wave with amplitude 5, a period of 10, shifted left 5 units and down 2 units, with our midline being on the line y equals to -2. So we can identify all of those parts and put it back together all in one problem, similar to what we had when we were shifting functions in general. All right, so if we can do it forward, we should also be able to reconstruct a formula given a graph. So determine the formula for the cosine function in the graph. All right, so we start looking at this. We have our max value here, and our max value is at y equals 5. We have a min value here of -1. So the number halfway between -1 and 6 is, or -1 and 5 is 2. So this is going to be our midline, y equals to 2. Well, the midline also corresponds to our vertical shift. So our vertical shift is 2, so that tells us that d is equal to 2. We then look at the distance from our midline to our max and our min. So the distance from our midline to our max and our min is the amplitude. And in each of these cases, it's going to be 3. So the distance from the midline So this tells us that our amplitude, or our A, is going to be 3. So our graph starts at 1, goes down to -1, comes back here. So this distance is our period. And our graph did not repeat itself until we got to 6 pi. So our period for this graph is 6 pi. And we know the formula for the period is the following. So our period is equal to 2 pi divided by b. So that gives us 6 pi is equal to 2 pi divided by b. So we could solve the absolute value equation and get two different values, but this is a cosine function. Cosine starts at 1, decreases to -1, and comes back up. So we did not reflect our graph, so we're going to conclude that it's positive. So we get 6 pi is equal to 2 pi over b. We multiply both sides of the equation by b. So 6 pi b equals 2 pi. Divide by 6 pi. Divide by 6 pi. And we get b is equal to 1/3. All right, so now we have our b is equal to 1/3. And our graph has no phase shift. Because the cosine of 0 is supposed to be 1. And so we didn't move right or left. We have our max right on our value. So our c equals 0 because there's no phase shift. So if that's the case, we have y equals a times the cosine of bx take away c plus d, which is going to give us y equals to, so our amplitude is 3 times cosine of our b is 1/3 x, and then our graph was shifted up 2 units, plus 2. So the formula that would graph that wave would be y equals 3 cosine of 1/3 x plus 2. So just as a recap, the way we broke that down, the first thing we did was find the midline by using the max and the min values and going halfway in between them. That allowed us to identify the amplitude of our wave. Once we had our amplitude, we then looked for where it started repeating. That gave us our period. Once we had the period, I didn't explicitly mention it, the midline tells us what the vertical shifting is. We found the amplitude, and then we found the period by finding when the wave started to repeat itself and used our formula that the period is equal to the absolute value of 2 pi divided by b, solved for b. In this example, there was no horizontal shifting, but we would have to know that the horizontal shift would be that we know cosine of 0 gives us 1, or the maximum value, and then we would have to figure out, did we go right or left from that point. All right. Let's take a look at our next example. The London Eye is a huge Ferris wheel with a diameter of 135 meters, and it completes a rotation every 30 minutes. The riders board from a platform 2 meters above the ground. Express the rider's height above the ground as a function of time in minutes. So let's draw a picture of what's going on here. So here's our ground. They have a platform. We know that the distance to the platform from the ground is 2 meters. They get on the Ferris wheel. So something like this. And we know that its diameter, so the distance all the way across, is going to be 135 meters. Well, the radius, which is what we're really going to want, is going to be half that distance. So our radius is 135 divided by 2, which is going to give us 67.5 meters. So now, when we start, they're going to start at a height of 2 meters. So that gives us that their min and what's the max going to be? Well, that would be when they're straight up. And if the radius is 67.5 meters, and the diameter is 135, what's the max going to be? Well, if this is 2, and the distance all the way across the circle is 135, the max is going to be 2 plus 135, which is 137 meters. So if that's the case, the min is at 2 and the max is at 137, where's the midline? So the midline is y equals 2 plus 137 over 2, which is 139 over 2, which gives us 69.5 meters. So the next thing we know is the period. So how long does it take for this Ferris wheel to go around one rotation? 30 minutes, right? So the period is 30 minutes. So then our period, so P is equal to 2 pi divided by B. So 30 minutes is equal to 2 pi over B. Gives us that B is equal to 2 pi over 30, so pi over 15. So then the amplitude of our wave is going to be the distance from the midline to the max or the min, which is also going to be the same as the radius of this. So the amplitude is going to be the distance from our midline, which is 69.5, to our min, so then putting all of this together, we get y equals 67.5 not quite, sorry, jumping ahead. So where does our, so we're starting, so we start at the min, which is 2, and after half of a period, we're at the max, which is 137. So let's go back and look at our first two functions that we did at the very beginning. So with the sine function, we started at 0, we went up to 1, came back down to 0, did this. So we didn't start at our min and go to our max. With the cosine function, we started at our max and went to our min. Okay, so neither of those are quite right. Turns out we can use either one of these to do the model. So if I were to shift this graph this way, how far would I have to shift it to the right to make me start at the min? So remember, the pattern continues back here. So it's going to have its min back at negative pi over 2. So if I shift this graph right a quarter of a period, we should be okay. So we can shift or if you wanted to use the cosine, we would have to shift it either right or left. But to get it to start at its min value is at pi, so I could either shift it right pi units or I could shift it left pi units. So with cosine, we would have to go either right or left pi units. Half a period. And the reason we can go right or left is because pi is half of a period. So in terms of sine, we would have y equals, our amplitude is 67.5 times the sine, and our period was pi over 15 times x, but then we have to shift it a quarter of a period to the right. So remember, our shift is c divided by b, but we know b has to equal to what our shift is, which is a quarter of our period. And our period was 30 minutes. So C over B has to equal quarter of our period, so 1/4 times our period, which is 30 minutes. We know our value of b, and our value of b is pi over 15. So c equals pi over 15 times 15 over 2. So we multiply both sides by pi over 15, and we get c is pi divided by 2. So putting that in, minus our pi over 2, plus our midline, which is 69.5. All right.